Hey everyone, today I want to talk about a neat classification algorithm I just learned in my machine learning class called Winnow. Let's first go over a high-level look at what the algorithm aims to do, and then we'll talk details. So, what are the general steps of the algorithm? Well, step one is the learner receives an example corresponding to a Boolean vector xt. Now, what is a Boolean vector? Well, a vector is just basically a collection of values, so kind of like an array, and this is a Boolean vector, so it's basically a collection of Boolean values. Now, you may also be wondering what the superscript t means, and the superscript t is basically just an index that refers to which vector this is in the collection of vectors we're feeding to the learner. So that's step one. Basically, give the learner a Boolean vector. Now for step two. Step two is the learner makes a prediction for xt by assigning a label of 0 or 1. And this is sort of the important step in my opinion, or I guess it's the goal of the algorithm, is we're trying to basically classify or categorize these Boolean vectors by assigning the correct labels. So essentially, if xt is predicted to be in the particular category that we're talking about, then the algorithm is going to predict a 1 or assign a 1. And if the algorithm is going to predict that the Boolean vector xt is not in the category, then it's going to assign it a label of 0. And our hopes for the algorithm is that the learner is going to assign as many correct labels as possible to the incoming data or the Boolean vectors. So that's step two, is once we receive the data, we're going to assign it a label. And this is basically why this is a classification algorithm, is because we are classifying or categorizing the incoming data. Okay, now for the final step, step three. Step three is the learner is told whether or not the label is correct. And this is actually the step that is going to allow the algorithm or the learner to improve on future iterations. It's going to receive feedback on whether the label was correct. And if the label was correct, then we're not going to do anything. But if the label was incorrect, and there are actually a few ways that the label can be incorrect, then the learner is going to modify a few things about its parameters in order to hopefully do better on the next run of the algorithm. So that's a general overview of the Winnow algorithm, and now let's go ahead and talk details. So there are actually two versions of the Winnow algorithm, which are very creatively named Winnow-1 and Winnow-2. So let's first go over Winnow-1, and then we'll discuss Winnow-2. Firstly, we need to go over what rule the algorithm will be using to decide which label to assign a given xt. To understand this rule, first consider the function f of xt. So xt is the incoming Boolean vectors. This is going to be equal to the sum from 1 to d, where d is the number of elements in the given xt, and it's going to be the sum of the wi's times the xi's. Now, what are the wi's and the xi's? Well, the xi's are the individual elements or the Boolean values of the given xt, and these xi's actually have a name. They're called features. So let me go ahead and write this down. These are the features, and actually these xt's or the Boolean vectors also have a name. These are called feature vectors. So there's a little bit of the terminology for you. Now, what are the wi's? Well, the wi's are what are called weights. So I'll go ahead and write this down. These are the weights. And the weights are exactly what we're trying to guess or predict using this algorithm. So in other words, the learner is attempting to learn the correct weights in order to produce the correct labels or categorizations. And this brings us to how our learner will decide on a label. The function that determines the label that will be assigned to a given xt is called a hypothesis. The hypothesis function for the Winnow-1 algorithm is as follows. It's going to be h of xt, where h means hypothesis, and xt is again our Boolean vector. And this is going to be a piecewise function because we have a few options. So is going to equal 1 if f of xt, which is the function we were just talking about, is greater than theta, and it's going to be equal to 0 otherwise. Okay, so what the hell is theta? I didn't define or talk about theta anywhere before this. Well, theta is what's known as a hyperparameter, and it's a value that we give to the algorithm. So essentially, theta is just some threshold value that determines which label is produced, and it requires us to tune this value. Okay, so now we know how Winnow-1 is going to be determining which label gets assigned to a given xt, so now let's actually jump into the algorithm. Alright, so what's step 1 of the Winnow-1 algorithm? Well, step 1 is to initialize all of the weights to 1. And notice that I put a decimal point here because I wanted to emphasize that the weights can take on non-integer values. So they can take on like 1.8, 2.75, whatever real number, I guess. Okay, so we're initializing all of the weights to 1 to start with as sort of a baseline, and then as the algorithm continues on, we'll be modifying those weights based on our predictions. Okay, step 2 is set the hyperparameters theta and alpha. So we've already talked about theta, but what is alpha? Well, alpha is another hyperparameter, and that hyperparameter is actually going to be what we use to modify the weights later in the algorithm. So we'll get to alpha later, but for now, just know that it's another hyperparameter that we are feeding to the algorithm, and we have to fine tune it just like theta to get good predictions. Okay, step 3 is assign a label based on the hypothesis function h. Now, if you recall, the hypothesis function is this function right here. It's h of xt, and it is evaluating f, and if f is greater than theta, then it's going to assign a label of 1, and if f is less than or equal to theta, it's going to assign a 0. And again, how f works is it is basically taking the product of weights and features, so weight feature pairs, and then it's summing those all up. So if that sum is greater than theta, it assigns a label of 1, and if it's less than or equal to theta, it assigns a 0. So step 3 is basically just actually making a decision on which label we're assigning to our Boolean vector. Okay, now for step 4. And step 4 is the important step, and it's also the most complicated step, because there are actually 3 possibilities or 3 branches that we can take depending on the current conditions. So let's go over the first scenario. The first scenario occurs, or 4.1 occurs, if the prediction was correct. And in this scenario, we don't modify any of the weights. Now, why not? Well, if our prediction is correct, then why modify the weights, right? There's no reason for us to decrease or increase the weights because our prediction was correct. So as far as we know, the weights are in the right spot. So that is why in this scenario, if the prediction was correct, we don't modify any of the weights. So that is the first possibility. Now let's talk about 4.2. The second possibility occurs if the learner predicts a 0, but the correct answer is 1. And in this case, we're going to undergo a process known as promotion. And this process is actually the process of changing the weights. And the purpose of changing the weights is to hopefully get a better prediction on the next run through. So let's talk about what happens during promotion. We're going to take all of the individual weights and we're going to reassign them. Now, what is the rule for reassigning them? Well, there's a few options. The first option is we're going to multiply the weight by alpha if the feature associated with this weight is equal to 1. And then the other possibility occurs if the feature is not equal to 1, and we're just going to assign the weight back to itself. So it's going to be wi otherwise. So let's talk a little bit more about this process. So why are we multiplying it by alpha if the feature associated with the weight equals 1? Well, alpha, I didn't really mention this before, but alpha needs to be greater than 1. So essentially, in this case, we are going to be increasing the weights. Now, the reason why we're increasing the weights is because we predicted too low, right? We predicted a 0, but the correct answer was 1. So as far as we know, on the next time, we should increase the weights a little bit because, we have one more example of the correct answer being 1. So we want to increase the weights to hopefully increase our answer potentially. So that's why we're multiplying it by alpha or a value greater than 1, is we want to increase the weights or increase the chances that we predict a 1 in the future. Now, why are we only doing this on features that are equal to 1? Well, if we go back to our function up here, f of xt, and we take a look at what it's doing, well, we have wi times xi in this sum. Now, if xi, or the feature, was equal to 0, then regardless of what the weight was, this entire product term must have been 0, which means that it didn't contribute to this overall sum, and that means that it could not have been a reason why our prediction was incorrect. So that's why we use this rule down here, where we only change the weights that are associated with features equal to 1, because if it was associated with a feature equal to 0, then it didn't contribute to our prediction in any meaningful way. Okay, perfect. So that is the process of promotion. If the learner predicts a 0 but the correct answer is 1, we're going to reassign the weights according to this piecewise function. Now let's talk about the last possibility, or 4.3. If the learner predicts a 1, but the correct answer is 0, so this is just the opposite of 4.2, or the last step we just talked about, then we're going to undergo the process of elimination, which is another process to modify the weights. Now, what is the process of elimination? Well, it's just going to be another piecewise function that we're going to use to modify our weights, and the possibilities are we're going to assign the weight to 0 if the feature associated with the weight is equal to 1, and we're just going to assign the weight back to itself otherwise. Now, what exactly is going on here? Well, we're basically reducing the weight, or reducing it to 0, if the feature associated with it is equal to 1. And remember, we do that because if the feature is equal to 0, then it's not going to change the sum. Now, why are we changing it to 0? Well, we're changing it to 0 because that's going to decrease the overall weights, and it's going to give us a higher chance of predicting a 0 in the future. Because if we arrived at this scenario, we just received another example that resulted in a 0. So we want to go ahead and predict 0 in more cases in the future, basically. Now, this is actually the main weakness of the Winnow-1 algorithm, is that elimination is actually far too extreme to get, decent predictions. Because notice that when we change the weight to 0 and we run back through the algorithm, if we start undergoing promotion, well, the weight is equal to 0, so no matter what alpha is, this product alpha times wi in the case of promotion will just equal 0. So basically, we're changing the weight to 0, and we're never going to be able to recover this weight. This weight will always equal 0 on future iterations, which is actually far too extreme. So that's actually the main benefit of the Winnow-2 algorithm, which we're going to talk about next, is we are going to be replacing the process of elimination with something better. All right, and that brings us to Winnow-2. And Winnow-2 is actually exactly the same as Winnow-1, but we're going to replace the process of elimination with the process of demotion. So in the case in Winnow-2 that the algorithm or the learner predicts a 1, but the correct answer was 0, we're going to go ahead and follow the process of demotion instead. So what is demotion? Well, it's going to be another process of reassigning the weights, and it's a piecewise function. But in this case, we're going to be assigning the weights to the weight divided by alpha if the feature associated with the weight equals 1, and we're going to be assigning it back to itself otherwise. So notice that this is extremely similar to the process of elimination, but the difference is that we're not just setting the weight to 0 if the feature associated with it is 1, we're dividing it by alpha, so we're just decreasing it by some positive amount, but we're not setting it to 0. So the difference between elimination and demotion, and the reason why demotion is better, is because these weights are not going to equal 0 after demotion, so we can actually increase them back in the future if we need to. So essentially we don't have the problem of, under predicting a bunch since we're not setting the weights to 0. And that is the process of demotion, and that's what makes Winnow-2 better than Winnow-1. Okay, that was probably a lot to take in, and it's probably going to be pretty hard to grasp how the algorithm is actually working unless we go ahead and run through an example. So in this example, I want to run through an instance of the Winnow-2 algorithm, and hopefully this helps you understand how the algorithm is working a little bit better. So the first thing that we need to know before starting the algorithm is, what are we actually trying to learn? What are we trying to get our learner to predict? Well, the thing we want to learn in this example is this Boolean expression. We have the term x1 or x2 ANDed with x3, and we want to try to predict the correct truth values for this expression based on our Boolean vector, which is basically going to be the vector containing x1, x2, and x3. So that's what we're trying to learn. And then notice that I also have the hyperparameters theta and alpha set right over here. I have theta set to 0.5 and alpha set to 2. And just to recall, theta is the threshold parameter that helps us determine which label gets assigned. And then alpha is the parameter we use to modify the weights. So we have the hyperparameters set right here. And then now let's go ahead and talk about this table. So we have x1, x2, and x3 here, which represents our incoming Boolean vector. And notice that I have every single possible input combination for x1, x2, and x3. I've got 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on. And there are 2 to the third possible input vectors for 3 binary digits. And then to the right of that, we have the 3 corresponding weights. We have weight 1, weight 2, and weight 3. And notice that to start out, they're all set to 1, because that's step 1 of the Winnow algorithm, is to initialize all weights to 1. So we have the weights figured out for us for the first iteration of the algorithm. Next, we have the prediction column, which is where we're going to put our labels. And remember that we are going to determine our labels based on our hypothesis function, which we'll go back to later. And then finally, we have our correct answer column, which just has all the correct answers. And remember that we're going to be feeding this back into the algorithm to modify our weights. So that's all of the stuff on the screen. And let's go ahead and start getting into the algorithm. So let's run through the first iteration. We've already got the weights set and we've already got the hyperparameters set. So we're going to start on step 3, which is to assign a label to the Boolean vector. So let's recall how we do this. So we've got the Boolean vector 0, 0, 0, and we have our weights. So we need to go ahead and evaluate f. And remember, f is this function right here, where we are going to take the product of all the weight feature pairs and then sum them all up. And then if it's greater than theta, assign 1. And if it's less than or equal to theta, we assign 0. So let's go ahead and go through that process. So let's go ahead and take the product of all of the weight feature pairs. We've got x1 times w1, which is 0 times 1 equals 0. And then we have x2 times w2, which is 0 times 1 is equal to 0. And then we have x3 times w3, which is 0 times 1 is equal to 0. So all 3 products are equal to 0, so we have 0 plus 0 plus 0, which equals 0. So we have the value 0, and 0 is less than theta, or it's rather less than or equal to theta. So we're going to predict a 0 according to our hypothesis function. Now, in this case, I want to note that a prediction of 0 is going to correspond to false, and a prediction of 1 is going to correspond to true. So we've predicted a 0, or false in this case, which was correct. The correct answer was false. So according to the Winnow-2 algorithm, we're going to not modify any of the weights and just repeat step 3 and 4. So let's go ahead and move on to the next Boolean vector then. We have 0, 0, 1. Now, to make this a little bit faster, notice that if the feature is equal to 0, then it doesn't matter what the weight is going to be. If we multiply the 0 feature by any weight, it's just going to equal 0. So we can just not do the products for features that equal 0. So we'll only focus on products where the feature equals 1, which in this case is just x3. So we're going to do x3 times w3, which in this case, let me go ahead and write in the weights again. 1 and 1 and 1. So we have x3, which is 1, times w3, which is 1, and that equals 1. 1 is greater than theta, so we're going to predict a label of 1. And remember that 1 corresponds to a truth value of true. So in this case, we predicted a 1, but the correct answer was false or 0, so we predicted incorrectly. And if we go back to the Winnow algorithm, let's figure out which case this is. Well, we predicted a 1, but the correct answer is 0. So we need to undergo elimination, or I guess rather, since we're doing Winnow-2, we need to undergo demotion. So let's go ahead and do that. So we need to undergo demotion on our weights. So essentially, for all of the weights associated with a feature equal to 1, which in this case is just x3, so we're only going to be modifying weight 3, we're going to take weight 3 and divide it by alpha. So in other words, we're going to take 1 and divide it by 2, and that equals 0.5. So we're going to replace weight 3 with 0.5 on the next iteration, and then weight 1 and weight 2 remain the same because they were associated with features equal to 0, so we don't modify them. Okay, so we've modified our weights and we can now proceed to the next vector, which is 0, 1, 0. Now the only weight feature pair that's going to contribute to the sum is x2 and w2 because x1 and x3 equals 0. So we have x2, which is 1, times w2, which is 1, and that equals 1. 1 is greater than theta, so we're going to go ahead and predict a 1 again. Now, notice that our prediction is incorrect. We predicted a 1 when the correct answer was false, or 0. So we know we need to go ahead and do demotion again. So we need to take the weight value pairs where the, or sorry, not weight value pairs, the weight feature pairs where the features are equal to 1. So in that case, that's just x2 at w2. And we need to modify that weight by dividing it by alpha. So we have w2 divided by alpha, which is 1 divided by 2, or 0.5. And then we don't modify the other weights. Okay, let's move on to the next vector, which in this case is 0, 1, 1. And remember, we're only going to be dealing with the features equal to 1 because features that equal to 0 do not contribute to the sum. So we have x2 times w2, which is 1 times 0.5, which is 0.5, and then plus x3 times w3, which is 1 times 0.5, which is 0.5. So we have 0.5 times, or sorry, 0.5 plus 0.5, which is equal to 1. 1 is greater than theta, so we predict 1. Okay, cool. So we predicted a 1, and the correct answer was true, or 1. So in this case, we actually predicted correctly, so we're not going to modify any of the weights. So let's go ahead and just move our weights down to the next row, 0.5, 0.5. Okay, perfect. Let's evaluate the next vector. The next vector is 1, 0, 0, so we're only going to use feature 1 and weight 1. So we're going to do 1 times 1, which equals 1. 1 is greater than 0.5, so we're going to predict a 1. Notice that the correct answer is false or 0, so we predicted incorrectly. So we need to go through the process of demotion again. So the only weight feature pair where the feature is equal to 1 is x1 and w1, so we're only going to modify weight 1. Weight 1 divided by alpha is 0.5, so we're going to replace weight 1 with 0.5. So let's go ahead and move these down, and let's do the next vector. So we're going to use x1 and x3 this time. So we've got x1 times w1 is 0.5, plus x3 times w3, which is 0.5, which is 1. So 1 is greater than theta, so we are going to predict a 1. And in this case, we predicted correctly because the correct answer is true, or 1. So we're not going to modify any of the weights in this case. So let's go ahead and drop our weights down to the next row, 0.5. Okay, cool. Now we're going to move on to the vector 1, 1, 0. So we're going to be using x1 and x2, but not x3 in this case. So we have x1 times w1 is 0.5 plus x2 times w2, which is 0.5, which is 1. 1 is greater than theta, so we predict 1. Notice that the correct answer is false, so we predicted incorrectly, and in this case we need to do demotion again. So we're going to modify the weights associated with features equal to 1, which are weights 1 and weights 2. So weight 1 divided by alpha is 0.25. So we got that right there. And then weight 2 divided by alpha is 0.25. And then we're not modifying weight 3, so we just drop it down as 0.5. And here is the last row. So we're going to evaluate the vector 1, 1, 1. So we're going to use all of the features in this case. So we have weight 1 times x1, which is 0.25, plus weight 2 times x2, which is 0.25, plus weight 3 times x3, which is 0.5. So we have 0.25 plus 0.25 plus 0.5, which equals 1. 1 is greater than theta, so we predict 1. And in this case, we were correct, so no weights are modified. And even if we were incorrect, we don't modify the weights anymore because there are no more vectors to evaluate. And that is the process of going through the Winnow-2 algorithm. We have modified the weights depending on our predictions, and we've gone through all input vectors. And next, I want to go ahead and show the same table, but using the new weights we've tried. Because now that we've actually accumulated the correct weights, it's actually going to predict the correct answer every single time on the next run through. Okay, so now I want to go ahead and run through the algorithm with our newly accumulated weights, and we're going to see how accurate we are after obtaining these new weights. So let's go ahead and do this very quickly. So none of this is going to add up in the sum because all the features are 0, so we predict 0. 0 is correct, so we are not going to modify the weights. So we put 0.25, 0.25, 0.5. Okay, the only feature that matters to the sum is x3, so we're going to do x3 times w3, or 1 times 0.5, and 0.5 is less than or equal to theta, so we predict 0. 0 is correct, so we don't modify the weights. So we move the weights down, 0.25, 0.25, and 0.5. Now we do x2 times w2, which is 0.25. 0.25 is less than or equal to theta, so we predict 0, which is correct. So we don't modify the weights. 0.25, 0.25, 0.5. Okay, now we do x2 times w2, which is 0.25, plus x3 times w3, which is 0.5. So that's 0.25 plus 0.5, which is 0.75. 0.75 is greater than theta, so we predict 1, which is correct. So we drop our weights down. 0.5. Okay, now we do x1 times w1, which is 0.25. 0.25 is less than or equal to theta, so we predict 0, which is correct. So we drop our weights down again. Now we do x1 times w1 is 0.25 plus x3 times w3, which is 0.5. That results in 0.75, which is greater than theta, so we predict 1, which is correct. So we bring our weights down, 0.5, okay. Now we do x1 times w1, which is 0.25, plus x2 times w2, which is 0.25, so that's 0.5. 0.5 is less than or equal to theta, so we predict 0. And that is correct. So now we move on to the last vector without modifying any of our weights. So we do x1 times w1, which is 0.25, plus x2 times w2, which is 0.25, plus x3 times w3, which is 0.5. That all added together equals 1. 1 is greater than theta, so we predict 1, which is correct. Now, I want you to sort of take a minute and just like think about how mind-blowing that is. After we ran through the algorithm one time on all the vectors, all of the weights were just completely correct. We completely predicted this Boolean function with 100% accuracy after running through that algorithm. Isn't that crazy? I mean, I think it's crazy, but maybe you don't. I don't know. But yeah, anyway, I think that's about it for this video. We covered the general steps of the Winnow algorithm. We covered Winnow-1 and Winnow-2 and some of the differences between them. And then we ran through an example. Thanks for watching.